Every AI prompt looks weightless on a screen. Behind it is a physical chain built with copper. Mines, smelters, refineries, cables, transformers, motors, cooling equipment, server power systems, and transmission lines. S&P Global's 2026 study projects global copper demand rising from about 28 million metric tons in 2025 to 42 million by 2040. Without meaningful supply expansion, it sees a potential 10 million ton shortfall. AI is not the only driver. Electrification, grids, vehicles, and industrial growth matter too. But AI adds demand at several layers at once, from the data center to the power system that feeds it. Start at the utility connection. Copper appears in transformers, switchgear, busbars, cables, backup generators, cooling motors, and building systems. Inside the facility, it carries power from medium voltage equipment to uninterruptible power supplies, power distribution units, racks, and boards. Beyond the campus, new generation and grid upgrades require still more metal. The exact amount per data center depends on design and on how much aluminum substitutes for copper. That is why simple copper per megawatt figures can mislead. The correct boundary includes the site, upstream electricity infrastructure, replacement cycles, and the broader competition for the same material. S&P frames copper demand through four major vectors: the energy transition, digital and AI infrastructure, mobility, and traditional economic development. These forces overlap. A renewable project needs grid connections. An electric vehicle needs charging. A data center needs both local electrical equipment and regional generation. The projected increase to 42 million tons by 2040 is therefore a system forecast, not an AI-only forecast. This distinction matters for investors and policymakers. Even if AI demand grows slower than expected, other electrification trends can keep pressure on supply. If several vectors accelerate together, the bottleneck becomes more severe. Copper supply cannot scale like software. S&P estimates a new mine takes about 17 years on average from discovery to first production. Developers must confirm geology, design the mine, secure permits, finance construction, build infrastructure, and manage environmental and community issues. Existing mines also face declining ore grades and rising costs. That long clock creates a mismatch with data centers announced for the next few years. Higher prices can encourage investment and recycling, but they do not instantly create qualified deposits or processing capacity. The copper market therefore translates a fast digital demand signal into a slow industrial response. The study's base path is stark. Total demand reaches about 42 million tons in 2040. Existing and risked primary mine supply peaks earlier and then declines as assets age. Recycling grows, potentially from about 4 million tons in 2025 to 10 million by 2040, but S&P says even aggressive recycling cannot close the entire gap. The remaining potential shortfall is 10 million tons, roughly 1/4 of projected demand. This is a scenario, not a certainty. Prices, substitution, new mines, efficiency, and policy can change the balance, but it provides a useful stress test for every copper-intensive investment plan. Copper is highly recyclable, which gives the market a valuable secondary supply route. Yet recycling depends on available scrap. Much of the copper installed in new grids, buildings, and data centers will remain in service for decades before it returns. Collection systems, sorting, processing capacity, and product design also determine recovery. S&P estimates recycling could provide about 1/3 of total supply by 2040 under aggressive improvement, still leaving a substantial need for mined copper. The practical strategy is not mining or recycling. It is both, combined with efficiency, better recovery, and smart substitution where electrical performance allows. Mining is only the first stage. Ore must be concentrated, smelted, refined, fabricated, and delivered in the form a manufacturer can use. S&P highlights geographic concentration in smelting and refining, estimating that 40 to 50% of total capacity is concentrated in China. That adds geopolitical and commercial risk even when mine supply appears adequate. Treatment charges, energy costs, and environmental rules affect which processors remain economic. For AI infrastructure, the relevant question is not only whether copper exists underground, it is whether refined metal and finished electrical products arrive in the right market at the right time. The opportunity spans miners, recyclers, smelters, refiners, cable manufacturers, transformer producers, electrical equipment companies, and engineering firms that reduce material intensity. But rising copper prices do not benefit everyone equally. Miners may gain while fabricators face margin pressure. Equipment makers with pricing power may pass through costs, others may absorb them. New mines can create value but also carry permitting, construction, and political risk. The strongest analysis follows contracts, cost curves, reserve quality, jurisdiction, capital intensity, and the timing of production. Copper scarcity is a system theme, not a one-ticker shortcut. Ask 5 questions. Is the demand number total copper or copper attributable to AI? Does it include upstream grid investment? Is supply counting operating mines, probable projects, or speculative resources? What recycling and substitution assumptions are embedded? And when does each project actually produce refined metal? Also separate a physical shortfall from a temporary inventory squeeze. Forecasts describe what happens if behavior does not adjust enough. Prices, technology, policy, and project execution can all change the outcome. A disciplined copper thesis states its boundary and scenario instead of treating the largest number as inevitable. Copper turns the AI story into an industrial one. The metal links generation to grids, grids to campuses, campuses to racks, and racks to processors. Demand is rising across several sectors while mines and processing capacity move on long development clocks. That does not guarantee a permanent shortage or a simple investment winner. It does mean that digital expansion is constrained by materials, infrastructure, and geography. Follow the full chain, or concentrate, refining, fabrication, equipment, installation, and operation. The next AI bottleneck may not appear in a chip benchmark. It may appear years earlier in a permit, a mine plan, or a cable factory.